April 2015, Washington delivered a decision that would alter the trajectory of South Korean air power for the next decade. The United States, as part of technology offset negotiations tied to Seoul's $6.8 billion F-35A procurement, agreed to transfer 21 of 25 requested technologies, but refused 4 critical systems outright. Those 4 were the AESA fire control radar, the infrared search and track system, the electro-optical targeting pod, and the radio frequency electronic warfare suite. The stated rationale was the preservation of advanced 5th-generation stealth capabilities exclusive to the F-35 platform. DAPA publicly confirmed the refusal on September 22, 2015, and Defense Secretary Ashton Carter reaffirmed the denial to Seoul's appeals in October of the same year. The impact on the KF-21 program was immediate and structural. South Korea had been counting on American radar architecture derived from the F-35's ANPG-81 lineage to underpin its domestic fighters' sensor suite. That foundation was now gone. Program managers at ADD faced a binary choice: abandon the ambition of an indigenous fire control radar or build the entire capability from scratch inside a compressed timeline. Seoul chose the harder path. The KF-21 program did not collapse. It pivoted, and that pivot would define the country's defense industrial identity for a generation. In August 2016, ADD formally designated Hanwha Systems, then operating as Hanwha Thele, as the lead developer for the KF-21's AESA fire control radar. The mandate was unambiguous: design, develop, and deliver a domestically produced gallium nitride-based X-band active array radar entirely within South Korean hands. Alongside, Hanwha League NIX-1 was assigned responsibility for the mission processing software stack, the algorithms, electronic beam steering logic, and combat mode architecture that transform raw antenna returns into actionable targeting data. The Agency for Defense Development retained program oversight, test planning, and systems integration authority throughout. The development program ran from August 2016 to August 2020. 4 years of hardware iteration, GaN module fabrication trials, and near-field antenna chamber testing at Hanwha's Yongin Research and Development Center. In August 2020, Hanwha unveiled the first AESA prototype, a milestone that validated the basic hardware architecture: roughly 1,100 gallium nitride transmit-receive modules, arranged in an X-band antenna array with electronic beam steering across a 120-degree field of regard. The unveiling was a proof of concept, not a finished product. The prototype could demonstrate fundamental radar function, but it had not been validated in the air, had not been verified against performance requirements, and had not confronted the manufacturing consistency demands of a production-scale program. Those challenges would require outside expertise. On May 23, 2017, 3 years before the Korean prototype even rolled out, ADD had already moved to hedge its developmental risk. A contract valued at approximately 40 billion Korean won, equivalent to $35.5 million US, was signed between ADD and Elta Systems, the radar and electronic warfare division of Israel Aerospace Industries. The official description of the contract, as announced by DAPA, was precise and deliberately bounded: support for the operation test of a prototype radar, not the development itself. Israel brought to the table something the United States had refused to provide and that Korea had not yet accumulated on its own: the hard-won industrial knowledge of a nation that had independently developed and operationalized AESA radar systems under combat conditions, free of American ITAR controls and export veto rights. The Israeli involvement deepened after the 2020 prototype rollout. At the Seoul ADEX Defense Exhibition in October 2021, Hanwha Systems signed 2 separate partnership agreements with Israeli firms. The first was with Elta Systems, encompassing AESA work, prototype manufacturing support, and the joint pursuit of export opportunities for Korean radar technology. The second was with Elbit Systems, encompassing broader aviation technology cooperation and unmanned systems. Flight Global's reporting confirmed that Elta was involved in producing the radar prototype and was understood to be participating in airborne test operations. The precise technical boundary between Elta's contributions and Hanwha's core design authority remains one of the most carefully guarded ambiguities in the entire program. DAPA insists the 2017 contract covered test support only, while industry reporting suggests a deeper prototype manufacturing role. Before the radar could fly inside a KF-21, it needed to fly at all. A modified Boeing 737-500, registered ZSTFJ and operated with South African logistical support, was configured as an airborne radar testbed. Beginning in November 2022 and running through February 2023, this aircraft conducted 18 test flights over the Yellow Sea, evaluating 25 specific air-to-air performance items, including maximum detection range against standard radar cross-section targets, multi-target tracking fidelity, and fire control accuracy at extended range. The full test plan, as designed, called for 62 evaluation items across approximately 50 flights, a scope that extended well beyond the 737 phase and into subsequent integration testing on the KF-21 airframe itself. The 737 program was a high-efficiency solution to a complex problem. Rather than waiting for the KF-21 prototype airframe to be available and instrumented, Korea used a large, stable commercial testbed to generate high-quality radar performance data quickly, at lower cost and risk than fighter-integrated testing would have allowed. The South African aircraft connection introduced an element of geographic flexibility, keeping sensitive radar emissions data away from easily attributable Korean test ranges during the most critical validation phase. By February 2023, the air-to-air mode data collected from those 18 flights had given Hanwha and ADD the confidence they needed to proceed with full KF-21 integration. On March 4, 2023, the third of 6 KF-21 development prototypes lifted off from Sachon with the APY-016K AESA radar installed and fully integrated into the aircraft's avionics suite. The 84-minute sortie marked the first time a Korean-built active array radar had flown inside a Korean-built fighter aircraft, an event that collapsed 11 years of program ambition into a single operational data point. The integration itself had required Hanwha and KI engineers to resolve the mechanical and electromagnetic compatibility between the antenna array, the aircraft's nose radome geometry, the liquid cooling architecture, and the mission computer data bus. None of those challenges were trivial on a production timeline fighter program. Testing continued through 2023 and into 2024 with increasing fidelity and operational realism. DAPA reported in August 2023 that the radar had successfully tracked a target at a range of 87 kilometers, a milestone that validated the system's detection architecture against real airborne targets under representative atmospheric conditions. Extended testing addressed not only air-to-air modes, but also the early iterations of air-to-ground mapping using synthetic aperture radar, with reported resolution estimates of 0.5 meters at 50 to 70 kilometers, with range extending to 200 kilometers, figures that remain unverified in open sources. The Yongin Near-Field Chamber Facility validated the manufacturing process could produce consistent antenna array performance across multiple serial units, a non-trivial engineering achievement for any first-generation national AESA program. The radar that entered mass production carries the designation APY-016K. It is a solid-state gallium nitride active electronically scanned array operating in the X-band, spanning the NATO IJ frequency range from 8 to 12 GHz. The production configuration carries approximately 1,000 transmit-receive modules, each built around GaN monolithic microwave integrated circuits that offer meaningfully higher power density and efficiency compared to the gallium arsenide technology that equipped earlier generation Western radar designs, including the AN-APG-83 fitted to the F-16V. Open-source performance claims from Korean official sources and analyst assessments place the detection range against a 1 square meter radar cross-section target at between 130 and 150 kilometers, with marketing materials citing figures up to 200 kilometers under optimal conditions. The system supports simultaneous interleaved operation across air-to-air, air-to-ground, and air-to-sea engagement geometries without mode exclusivity. Air-to-ground modes include real beam ground mapping, Doppler beam sharpening, ground moving target indication, and SAR mapping at multiple resolution levels. The electronic warfare architecture is noteworthy. Some TR modules within the array can be reprogrammed to emit directed jamming waveforms, giving the radar a dual function as both a sensor and a localized electronic attack asset. Low probability of intercept waveforms are built into the signal processing baseline. Behind every transmit-receive module in the APY-016K sits a gallium nitride monolithic microwave integrated circuit. And for the first several years of the program, those chips came from foreign foundries, principally in the United States and Europe. That dependency represented the most technically sensitive remaining vulnerability in the Korean radar program. An AESA radar is only as sovereign as its semiconductor supply chain. On July 15, 2025, the Electronics and Telecommunications Research Institute, working in partnership with the Korean semiconductor firm Wavice, announced the successful localization of GaN MMICs for Airborne AESA applications, including power amplifier, low noise amplifier, switch, and single-chip integrated designs. The announced performance metrics placed the domestic chips on par with leading commercial products from American and European foundries. The strategic implication of that announcement was substantial. If production-scale KF-21 radars, the 40 units contracted for delivery between 2025 and 2028, are populated with domestically produced GaN MMICs, South Korea will have achieved end-to-end supply chain sovereignty for its most sensitive airborne sensor. Whether the current production batch already incorporates domestic GaN chips or relies on a transitional mix of imported and locally produced devices has not been officially confirmed. That single ambiguity represents the last major unresolved dependency in a program that has otherwise achieved remarkable levels of indigenous control. The answer will determine whether Korea can freely export its radar without triggering third-party re-export reviews from the original chip suppliers. On August 5, 2025, at Hanwha Systems Yongjin Research and Development Center, the first mass-produced APY-016K AESA radar was formally unveiled at a ceremony attended by DAPA, the Republic of Korea Air Force, and ADD. The production contract, covering 40 radar units for delivery between 2025 and 2028, represents the Block 1 operational baseline, equipping the first 40 KF-21 aircraft with air-to-air optimized sensor capability. On March 25, 2026, the first production standard KF-21 Boramae aircraft was rolled out at KIA's Sacheon facility, with its maiden production flight completed in April 2026. Initial deliveries to the ROKF are scheduled for the second half of 2026, with the full 40 aircraft Block 1 complement expected by 2028. Block 2 aircraft, encompassing approximately 80 additional units, planned to be delivered between 2029 and 2032, will receive full multi-mode radar capability through software upgrades that complete the air-to-ground and maritime engagement architecture. The weapons integration picture for Block 1 centers on European munitions, MBDA's Meteor Beyond Visual Range Missile, and the IRST Short Range Missile, specifically chosen to avoid American ITAR controls that would complicate export licensing and operational autonomy. Integration of American origin weapons has been deferred, in part because of the very technology control framework that originally denied Korea the radar it now produces domestically. In May 2024, Hanwha Systems signed a contract to supply AESA antenna components to Italy's Leonardo, with deliveries scheduled to begin in September 2025, a transaction that would have been impossible had the radar been built on American licensed architecture. On March 25, 2026, the first production standard KF-21 Boramae aircraft was rolled out at KIA's Sacheon facility, with its maiden production flight completed in April 2026. Initial deliveries to the ROKF are scheduled for the second half of 2026, with the full 40 aircraft Block 1 complement expected by 2028. Measured against its peer class, the APY-16K occupies the upper tier of 4th-and-a-half generation fire control radars. The AN-APG-83 Sabre fitted to the F-16V carries approximately 1,000 gallium arsenide TR modules and achieves detection ranges in the 120-kilometer class. The Korean radar's GAN architecture and larger aperture provide a meaningful efficiency advantage over that reference point. The F-35's AN-APG-81 fields 1,676 modules, integrates deeper into the aircraft's distributed aperture and electronic warfare architecture, and carries higher classification protection. But it is also a system South Korea was explicitly denied and cannot independently modify or export. China's KLJ-7A radar on the JF-17 Block 3 carries approximately 1,000 GAN modules, with range claims reaching 170 kilometers, placing it in direct performance competition with the APY-16K. The J-20's Type 1475 radar represents the upper bound of the regional threat environment, an array estimated at over 2,000 GAN modules, with detection range claims exceeding 200 kilometers, benefiting from the J-20's significantly larger nose aperture. The KF-21 does not match that capability and was not designed to. It was designed to dominate the 4.5 generation competitive space, to outperform upgraded legacy platforms, compete with peer nation 4th generation fighters, and avoid the political and technological dependencies that have constrained Korean air power autonomy for decades. Against that design intent, the APY-16K succeeds. The European Captor-E ECRS Mark II, entering service on the Eurofighter Typhoon around 2028 with a wide-area steerable field of regard, represents the closest Western analog. Similar module count, similar range class, but a decade-longer development timeline and full dependence on consortium export politics. What the KF-21 radar program formalized was not a transactional arms deal. It was the consolidation of a strategic technology partnership that had been building since the 1990s. Israel and South Korea share a structural alignment of interests that is rarely articulated in public. Both are technologically advanced democracies with capable defense industries. Both operate under permanent threat environments that demand continuous sensor and weapons development. And both have experienced the political costs of excessive reliance on a single great power supplier. Israel brought to the KF-21 program an AESA radar industrial base that had been developed entirely outside American ETRI jurisdiction, validated in operational combat environments, and refined through decades of independent system engineering. Beyond the radar, the partnership has expanded across the full spectrum of defense technology. The 2017 IAI Hankook Carbon Joint Venture targeted vertical takeoff and landing unmanned systems. The 2021 ADEX agreements extended cooperation into urban air mobility, loitering munitions, and export market development. A bilateral free trade agreement concluded in 2022 was accompanied by an $8 million annual joint research and development fund targeting artificial intelligence and semiconductor technologies, precisely the domains that will determine AESA radar performance evolution over the next decade. Korea has also sourced Italian Leonardo technology for the IRST Skyward K sensor, European MBDA and DEAL missiles for Block 1, and has advanced indigenous electronic warfare development with European technical inputs. The U.S. denial did not isolate Seoul, it diversified Seoul, building a multi-axis technology dependency structure that reduces exposure to any single supplier's political calculus. The KF-21 AESA radar program is not a story of technology theft, backdoor acquisition, or dependence replacement. It is a case study in how a mid-tier industrial power, confronted by a deliberate capability denial from its primary security patron, methodically built sovereign technological capacity by combining domestic institutional investment, selective foreign partnerships, and the patience to accept a longer development timeline in exchange for permanent program control. The United States made a rational, consistent decision in 2015, protecting its most sensitive fifth-generation sensor technology from proliferation. South Korea made an equally rational response, building the alternative with partners who had no veto over its operational decisions, its upgrade roadmap, or its export customers. Israel's role was not to hand Korea a finished radar. Elta Systems bridged the most technically vulnerable phase of the program, the gap between a domestic prototype that could demonstrate hardware function and a flight-validated system that could enter manufacturing scale-up. That bridge, valued at $35.5 million in its initial form and deepened through the 2021 partnership structures, was the catalytic investment that determined whether the entire Korean sovereign radar effort would succeed on schedule or slip by years under the weight of airborne validation failures. The ultimate product, 40 mass-produced APY-16K units entering operational service in 2026, carries Korean design authority, Korean manufacturing capacity, and Korean export rights. The refusal that threatened the program a decade ago has produced an outcome that Washington almost certainly did not intend: a Korean radar industry that is now competing in the international market, free of American re-export controls and growing in capability with every subsequent development cycle. As of April 2026, 3 questions define the unresolved boundary of what the public record can confirm. First, what specific technical data passed from Elta Systems to Hanwha during the 2017 to 2023 collaboration period? The line between prototype manufacturing support and substantive design transfer has never been publicly drawn, and its location matters for both attribution of the final product and assessment of any residual Israeli intellectual property embedded in production units. Second, whether the 40 radars currently in production contain fully domestically manufactured GaN MMICs from ETRI and Wavice, or whether imported chips from American and European foundries remain in the supply chain. A distinction with direct consequences for export licensing and long-term supply chain resilience. Third, what the APY-016K actually achieves against low observable targets operating below its nominal 1 square meter reference RCS. No public test data exists for this scenario, and it is the operational question that matters most in a theater where Chinese stealth platforms are entering service in significant numbers. What the record does confirm, unambiguously, is this: a nation that was told in 2015 that it could not have the technology will, by the end of 2028, have delivered 40 operational copies of that technology to its Air Force, built in Korean factories, designed by Korean engineers, sold without permission from Washington, and validated through a partnership with a nation that understood, better than most, that strategic self-reliance is not a luxury reserved for great powers. It is a discipline. And South Korea, over the course of a decade of refusals, technical setbacks, and methodical industrial construction, has mastered it.